welcome everyone to Dhyuti Spotlights. So before that, I would like to briefly tell what Dhyuti is all about. It's an open source community initiative to enable chasing hard problems in science and engineering in the AI era. So we have a Git organization where you could also check out some of our open science contributions, and also something that's evolving over time with more and more people joining into interested to contribute to various different aspects of scientific machine learning. And we already have a couple of micro challenges and open uh, first issues that we first time contributors can work on. And we also have a growing WhatsApp channel which started with just me, and now we have about 220 plus followers for the WhatsApp channel, where we share content related to scientific machine learning, announcements related to various walkthroughs and sessions and seminars that we organize, and anything else related to our activities and related to scientific machine learning. And so today I'm very happy to launch Dhyuti Spotlight, a different format compared to our Dhyuti talks and Dhyuti walkthroughs. So here, this is expected to be a platform to amplify voices of prolific young researchers who are just about to graduate or have graduated from their PhDs and on their journey to the next destination. And so today we have a great researcher, Dr. Smarak Rath, who also happens to be a very close and dear friend of mine from IIT Madras. And he, as far as I'm concerned, whenever I have interacted with him, I've always been inspired by his sound knowledge of material science from the foundations, from the fundamentals. And I've always really respected and valued such insights. And he has also had experience working on material informatics and also pure empirical experimental methods as well. So it will be really interesting to listen to him. And I'm handing over to Smarak to begin his talk. Thank you, Smarak.
Yeah, thank you, Rahul, for your kind introduction. And I'm very happy to be here and share with you guys what I have learned over the years. So, I worked on materials informatics in the initial part of my PhD, mostly in 2020 and 2021. And after that, I switched to experiments. So yeah, maybe the world has evolved and changed over these years. So many new things might have emerged, and it is always a good idea to follow up with your own research. But nevertheless, we will get started with what I have in mind. I will just share my screen, and yeah, so that okay. So are you guys able to see the PPT?
Yes.
Yes, yes.
Yeah. Okay. So I will be giving just an overview of materials informatics in this talk, and I will begin with the four broad paradigms of science. So the first paradigm of science which ever emerged was empirical science, in which people just did experiments. They just did whatever they could. It was all hit and trial, and that is how technology progressed for a very long period of time. People just did experiments like whatever they could without much forethought about why they were making the choices they were making. Then gradually people became more and more interested in explaining things like why is it that we are observing what we observe, like what is the explanation for this observation or that observation. So that is the second paradigm of science, which is theoretical science, in which scientists actively started pursuing scientific theories which are explanations of natural phenomena. So you have things emerging like classical mechanics, classical thermodynamics, etc. Then, with the advent of computers, we move to the third paradigm of science, which is computational science, uh, and people all over the world today carry out simulations using various software, And with respect to material science, I would like to highlight that the most popular simulation techniques are density functional theory and molecular dynamics, which I will be covering in more detail. Then the world has moved further, and we have a fourth paradigm of science now, which is data science. In like purely because we have generated huge quantities of data through experiments as well as simulations, we can now use that data to extract insights, and that is what data science is all about. So, first of all, I would like to highlight the difference between computational material science and materials informatics, which is the application of machine learning to material science. So, the in case of computational material science, no matter what simulation technique you use, whether it is density functional theory or molecular dynamics, the underlying scientific theory is always known. It is always concrete. For example, molecular dynamics is based on classical physics. The ultimate aim is to solve the Newton's equations of motion and map the trajectory of the atoms in the simulation box. In density functional theory, or DFT, is based on quantum mechanics, in which the ultimate aim is to solve something called Kohn-Sham equations. So, in this paradigm, the underlying scientific theory is concrete. That is not the case with materials informatics. These ML algorithms which we use, they learn everything from scratch, and no one uh, knows how exactly they reach the conclusions they reach. Like how exactly they learn, we don't understand that very well in all cases. So that is a crucial difference which we need to realize. Now, when it comes to density functional theory and molecular dynamics, there are some limitations which people should understand. And these are the limitations because of which people have moved increasingly towards materials informatics. So, molecular dynamic simulations, although widely used, cannot be used for for calculating electrical, magnetic, and optical properties of materials. So, uh, people involved in a variety of applications like materials for solar cell technology or spintronics or devices used in computers. These people need to measure electrical, magnetic, or optical properties as the situation demands, and molecular dynamics cannot be used for the calculation of these properties. So it becomes severely limited in certain applications. Now, DFT simulations are more versatile in that respect because they can be used for the calculation of electrical, magnetic, and optical properties. But the problem is that DFT's simulations are much more time consuming. The time taken by a DFT simulation scales as the order of n cube, where n is the number of atoms in the supercell. A supercell is just a uh, term for simulation box. The term simulation box is used in molecular dynamics, and the term supercell is used in DFT. In contrast, the time taken by a molecular dynamics simulation scales as the order of n. So DFT simulations are much more time taking than um, molecular dynamics simulations, and that's a major drawback. And in addition to that, DFT simulations are essentially zero Kelvin simulations because DFT is based on based on an approximation called Born-Oppenheimer approximation, where we assume that all the nuclei of all the atoms are frozen, absolutely frozen, which means that these are zero Kelvin simulations because at any temperature above zero Kelvin, the nuclei are going to vibrate. So that is another limitation of DFT around which we have to work. And so you can clearly see that there are limitations in both DFT and molecular dynamics. And that is why people have moved towards machine learning because ML algorithms, even when you feed a very large quantity of data can be potentially trained in a matter of minutes. In contrast, a DFT simulation can take months, 2 months or 3 months, let's say, if the number of atoms in the supercell is very high. So there is a clear advantage as far as the time is concerned. Now, machine learning can be utilized in various ways. One is property prediction. So let us say someone does not want to synthesize a material in a lab, because synthesizing materials can be very time taking. Getting a single phase of a material can be very time taking. So, to predict various properties of that particular material, the researcher can use machine learning. It can also be used for something called inverse design, in which, like, if you want the property of a material to be in a certain range, let us say you want the band gap of a material to be within, let's say, 2 electron volt to 2.5 electron volt, and you want to know like what are the compositions uh, which can have band gap in that range. So machine learning can be used for such an inverse design problem. So you specify a range and then you can get the compositions. Although this is a much more complicated problem, and I personally have not, I don't know how to execute this. Then machine learning can be used for discovering new science, and unsupervised learning is very useful for this purpose. And finally, extraction of knowledge from literature is something which people can do using natural language processing. So that is also something which is being explored. Now, this is something I think you guys already know, like what are the categories of machine learning. I won't be spending much time over here. So, yeah, this is the overall workflow of an ML problem. So it obviously starts with collection of data which is already available. Now data is available in research papers, of course, but there are various databases which you can access either for free or by paying a certain amount of money. And these databases also have a lot of useful information. Now, in case you don't have your desired data in either research papers or databases, you can always generate them using experiments or computation. And then the generation of features slash descriptors or slash fingerprints is a very important step if you want to achieve higher accuracy. And I will be coming back to this in a while. But let me just highlight some of the popular databases which I have encountered over the years. So these are a few examples. Inorganic Crystal Structure Database, or ICSD, is a very huge database which contains crystal structure information. This is a paid database. Crystallography Open Database is also a database containing crystallographic information, but this is absolutely free. So you are always, welcome to check this out. Then Materials Project is a very popular computational database. All the data in Materials Project has been generated using density functional theory simulations, and by far, this is the most popular DFT based database which I have encountered. Data various data related to various materials properties of more than 140,000 inorganic compounds are available in this database. Then there are other computational databases like aflowlib, nomad, which you can explore. Citrination used to be free, but now I think they have moved to the paid version, and so on and so forth. Like there are many others, but these are some of the popular ones which I have listed. The point is, if you have access to a good database, then your work becomes considerably easier. And one point which I would like to highlight here is, if given if you have a choice between experimental databases and computational databases, in my opinion, you should always go for experimental databases, because all these simulation techniques which are used by material scientists like DFT or molecular dynamics, they are based on various approximations, and only the people who are regularly involved in performing these simulations know a lot of details about these approximations. And so, as someone who is interested only in machine learning and not necessarily in these simulation techniques, it is very easy to lose track of these approximations which are involved in these simulation techniques. So when you lose track of these approximations, you might end up using data which can lead to incorrect predictions, and defeat your entire purpose. So in that sense, experimental databases are much more reliable because these unknown factors are not involved. So you know what has been calculated, and that is something which can't be disputed. So given a choice, I think experimental databases should be preferred. But again, like, there are data which are available only in computational databases in some situations, and in those cases we have to work with that. Yeah, there is another thing which people should know, that many databases offer an application programming interface, or API. APIs can be used to extract data from online databases with a high degree of convenience. For example, uh, for all these people who work on dielectric materials, the dielectric constant or relative permittivity is an important material property which they deal with. Now, if someone wants to design a data set for the prediction of dielectric constant of unknown, or let's say compounds which have been synthesized before, but like for which dielectric constant has not been calculated, it is not necessary that you just type the names of individual compounds one by one and see the dielectric constant value and note them down in an Excel sheet one by one. So all these data extraction processes are highly automated, and they can be done using APIs. For example, PyMatGen functions as the API of the materials project database, which I was just talking about. So very convenient. These APIs are very convenient, and you should definitely learn how to use the API of the database you are using. At least for the computational databases, these APIs are available for use. Now, I will discuss some of the factors affecting the accuracy of property prediction. Number one is the size of data set. Using large data sets is obviously desirable. Then there comes the choice of features or descriptors. If you use too many features, then that reduces the accuracy. Then comes the choice of algorithm. You should know something about the algorithms which you are using. It should not be like that, like during your PhD you are involved in a certain materials informatics problem and you are just playing around with different algorithms like a child. You need to have some depth in machine learning algorithms to just understand how these algorithms work and in what situations these algorithms might be useful, and hyperparameter optimization of the algorithm you are selecting. So hyperparameters are the internal variables of a certain algorithm which you might choose, and these internal variables have default values. Now, you might not get the highest accuracy using those default values. So you have to perform an optimization step, so that the optimized hyperparameters of that algorithm can be finally used to achieve the best possible accuracy. Now, over here, I would like to highlight some very important points, like especially about the size of the data sets which people use. It is crucial to note that materials informatics has not really entered the big data paradigm. Like the amount of data which we need to extract useful insights is actually very, very huge. And as far as material science is concerned, we don't have access to that kind of data. For example, a 2016 paper, I can actually show you that because I have it here on my laptop. So this is a 2016 paper which tells that every month more than 6 billion GB of video data is uploaded on YouTube, and that is in 2016, 9 years ago. So that is a huge amount of data, and when computer scientists deal with that kind of data, they can extract really powerful insights. Now, in contrast, when I talked about the materials project database, which is a computational database, you will find data for around 140,000 uh, inorganic compounds. That is not even half a million. It's half a million is 500,000. So that is not even half a million. You need millions of data points before you can have confidence in the insights that you are extracting. So this is a severe limitation with which material scientists are working right now. I mean, the people who are involved in materials informatics. So right now, the most important thing, in my opinion, is the generation of lots and lots of data and consolidation of all that data into organized databases. For example, I will just go back to a previous slide. If you notice in this list, there is a database called Citrination. So Citrination basically is a company which is involved full time in the generation of data, data materials properties, various materials properties. They generate data, by going through research papers, and they hire computational material scientists and whatnot. So they generate a lot of data, collect a lot of data from already existing research papers, and they consolidate that into a very organized database. It used to be free. I think they have moved to the paid version now. So this, in my opinion, is the most important thing which needs to be done right now. So unless any random material scientist has access to millions of data points, he or she cannot extract useful insights. That is simply not possible. And there are some people who have tried to master the skill of extracting insights from very small databases, but that is a very specialized skill. And if someone, let us say, is trying to do materials informatics research in his or her PhD, mastering that very specialized skill can itself take up a lot of time, and you may not be pursue the actual research problem you are pursuing. So extracting insights from very small databases, that is a very specialized skill, and some people are working towards that. But that is not a luxury which everyone can have, especially PhD scholars, in my opinion, because they have only limited time before their stipend runs out. And developing a very specialized skill and then starting to think about their research problem is not something they can afford. So we need companies like Citrination, which work full time on consolidating databases by collecting a lot of data, generating a lot of data. So that needs to be a serious activity, in my opinion. So that is the single most important challenge we face right now. And yeah, so just moving on, I will talk something about descriptors or features. Now, for those of you who might not be familiar with these terms, features slash descriptors are the input variables of an ML model. In contrast, the target property which you want to predict is the output variable of of an ML model. So if there are a set of input variables, let's say x1, x2, x3 up to xn, and let's say the target property is y, the ultimate aim of a supervised machine learning algorithm is to find out an objective function so that y can be expressed as a function of x1, x2, x3 up to xn. That is what the algorithm basically does. It finds out an objective function. And I am limiting myself to supervised ML algorithms right now. So the kind of descriptors you are using for your ML model is very important. And if you use too many descriptors, or let's say incorrect descriptors, then you will end up facing a lot of problems. And there are some basic features which these descriptors or features should capture. So they should capture the composition of a material. They should be, for example, able to differentiate between CuO and Cu2O. Uh, so there are descriptors like atomic fraction of various elements, which can be used in an ML problem. They should capture the properties of constituent elements like atomic number, atomic mass, atomic size, electronegativity, Mendeleev number, etc. And finally, they should also capture crystallographic information. They should be able to differentiate between various polymorphs of the same composition. Now, to put things in context, there are some materials which exist in multiple crystal structures. They don't show a single crystal structure, they show multiple crystal structures, and each of them is called a polymorph. So, uh, for elements, the term is allotropes. For example, carbon, it is said that carbon has multiple allotropes like graphite, diamond. So, these are different crystal structures of the same material, carbon. For compounds, the corresponding term is polymorph. So, TiO2, for example, has three polymorphs, which are anatase, rutile, and brucite. So, although the composition is the same, which is TiO2, all three polymorphs have different crystal structures. So, whenever you are using in your data set multiple polymorphs of certain compositions, so you might end up using a lot of materials in your data set, and some of these materials might have multiple polymorphs, and your descriptors should be able to differentiate between these polymorphs, because uh, the composition is exactly the same. If they are unable to differentiate between the various crystal structures, again, errors will be introduced. So these are some of the popular ML algorithms which are used by materials informatics people, and this is something you can explore easily on your own. Yeah. Now I will discuss some of the pressing challenges. So there are complex models like artificial neural networks, deep neural networks, which can give very high accuracy but are difficult to interpret. Simpler models, on the other hand, are easier to interpret but may not give high accuracy. So, uh, in the industry, it doesn't really matter why a certain algorithm is showing good performance, because ultimately the industry people are concerned with performance. Like if a certain algorithm let's say deep neural networks are performing very well, they are giving very high accuracy, then the job is done. They can be used for predicting whatever materials properties that particular company is interested in. And it doesn't really matter why that particular algorithm has the best performance, right? But for people involved in research, uh, PhD scholars or postdoc scholars or professors or scientists, for them, the interpretation part is important. So these are the people who actually struggle. Like they might find that ANN or DNN is giving very high performance, but these models are very difficult to interpret. And some progress, if it ever happens in that direction, will be a welcome thing, especially for researchers who are interested in explaining things. Then, then there is another important point. If one compares the value of a certain material property in different databases, the values may differ across databases. This is because a given material property can be measured using multiple experimental methods, and not just experimental methods. Even if you are dealing with computation, let's say density functional theory, I can give you the example of band gap, which is very important for solar cell technology. So band gap can be calculated using density functional theory, but there are multiple approaches which one can adopt. So one can use something known as GGA functionals. Then there are people who, in addition to GGA functionals, use something called Hubbard parameter. Then there are other people who use something called hybrid functionals. I will not go into the details of these things, but the point I am trying to make is there are multiple approaches involved in the calculation of the same material property. And this is true in computation and experiment. So, so if you are ever involved in materials informatics and uh, let's say you are reading research papers, it is important to know what are all the techniques which can be used to measure that material property. So let's say there is a material property which can be measured using 1, 2, 3, 4. It is important to know the details of all these four methods. If you are in the dark and you may end up taking data which, let's say, has been calculated using method 1, uh, you can take that kind of data for certain materials in your data set, and then for certain other materials you can take data which has been generated using method 2 or method 3, for example. So that kind of mixing is undesirable. So you should know what are the methods which can be used for measuring these properties. Again, now application of deep learning techniques is a challenge because large data sets are not easily available. This is something I've already discussed. A vital skill which researchers in materials informatics should have is the extraction of insights from small data sets. This is a very specialized skill, and people in PhD may not have that much time to develop such a specialized skill. But yeah, once you join some company, you already have a job and you can utilize your time to develop these skills. And so companies can also look for these kinds of skills when they are recruiting people. Application of unsupervised learning techniques, this used to be a challenge when I was involved actively, but I think this has made a lot of progress. I mean, you can always explore research papers. I think many more people are using unsupervised and machine learning techniques now. Uh, then there is another issue, which is prediction of properties which are highly sensitive to grain size. Yeah, this is important, especially for people who don't have a materials background. So there are uh, so whenever you synthesize a material, it is mostly a polycrystalline material, which consists of multiple grains or multiple crystals. So each each grain has a certain crystallographic orientation. But when you go to a different grain, the crystallographic orientation changes. For example, I will just give you one example to make things clear. I used to deal with a material during my PhD known as aluminum ferrite (AlFeO3), and that material has an orthorhombic crystal structure. And the point I'm trying to make is that when someone synthesizes polycrystalline aluminum ferrite, it will have multiple grains, and although all these grains have orthorhombic crystal structure, that is something which does not change. The crystallographic orientation can change from grain to grain. So when you go from grain 1 to 2, 3 to 4, the crystallographic orientation can change. And the grain size is an important uh, mu- parameter which people need to have in mind, because there are properties which are highly sensitive to grain size. For example, the yield strength or elastic limit of a material is highly sensitive to grain size. Again, for people who are not familiar with mechanical properties, I will just give a brief definition. The yield strength or elastic limit is the stress beyond which a material starts showing plastic deformation. So till a certain level of stress, the material will show elastic deformation. So whatever deformation the material experiences, if you remove the external force, the material will return to its original shape. But beyond a certain stress, the material shows permanent deformation or plastic deformation. So even if you remove the external force, the material won't return to its original shape. So there is a critical value of stress beyond which permanent deformation happens. And that critical value is the yield strength or elastic limit. And yield strength is something which is highly sensitive to grain size. As you go on decreasing the grain size, the yield strength of a material goes on increasing. So dealing with such material properties is a problem, because just imagine if someone is interested in predicting yield strength of materials, uh, of unknown materials, like for which they haven't been measured. He or she can always, try to design a data set, divide it into training and testing, the usual drill. But the point is, uh, you see, if there are multiple rows in that data set and each row corresponds to a certain material, you cannot specify a single value of yield strength for that material, because you see, the same material can show different values of yield strength at different values of grain size. So you cannot assign a single value of yield strength to a single material in that data set. So that is something which cannot happen. And for such problems, we need to come up with new methods, you know, some innovative solutions. But the first step is that you should be aware of these things. Whenever you are venturing into this space, you should be aware that there are certain materials like yield strength and even electrical conductivity, for that matter, which is important in a huge range of applications. There are material properties which are highly sensitive to grain size, and one has to be careful when dealing with such materials, because the approach will change when you are doing property prediction for such material properties. And yeah, so that is basically it. These are some insights which I wanted to share with you. And if there are certain questions which you have, I will be happy to answer them to the best of my ability.
Yeah, thanks, Marak. That was really great. I think for a dummy like me in material science, I think this is a very, very good overview of what material informatics is and what the pressing challenges look like, and also where we see the entire domain going towards. I really liked your opening slide about the different paradigms of, you know, material informatics or computational material science. I mean, that was very,
Yeah, yeah.
yeah, it was very, very. I mean, it clearly shows where we are heading towards as well. So, uh, and in fact, very recently there's been a 500 TB data set for, I think, DFT simulations, which about 100 million DFT simulations that have been released by Meta.
Oh, that is great. So they are consolidating that kind of data. That is great. That is
Yeah,
what.
yeah, yeah.
Yeah.
So it's about 500 TB,
Yeah.
500
Yeah.
terabytes of data sets. Yeah.
Yeah, I mean, even for experimental data, you see, there is a lot of data, but someone has to do the hard work of going through all those research papers one by one
Correct.
and consolidating that data and, building an organized data set. And that kind of thing is best done by companies. Like an organization is required to do such things. An individual PhD student is not does not have that kind of time. So uh, companies which have dedicated R&D divisions can
Hmm.
really take this forward, not
Correct.
just for computational stuff but for experimental
Yeah.
stuff as well.
Yeah. And the real delta also comes when they open source these data sets, and where researchers do not have to really pay for these data sets, and
Yeah.
it kind of democratizes the access to these kind of this information. Otherwise, you see a lot of this information, like you pointed out as well, is often logged in papers or in silos where there are specific labs holding these data sets, not releasing them, right? So you don't have access to some of the information or insights that have been derived from some of these smaller data sets. I think such open science, big science initiatives could really accelerate the trajectory towards discovery of better and newer materials, don't you think?
Yes, yes, yes. Yeah, I agree. I fully agree.
Yeah. And I really have another question before leave it for others to ask as well. So, if, so I think we are basically exploring a completely combinatorial space, right? So you had mentioned about how you might have polymorphs of materials, and you also
Yes.
have, which is basically the crystal structure. Then you also have the grain size. So let's say you have a particular crystal structure, you also have the grain size that you need to worry about, and then you also have these two things, and then also, yeah, the grain size depends on the temperature at which you nucleate and then you form the material itself, right? When you is it is it correct?
Yeah, 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 pretty much. Well, I was involved in synthesizing ceramic materials uh, as opposed to rather than metallic materials.
Mm-hmm.
So, for a layman, a ceramic is a solid inorganic compound.
Hmm.
It has to be a
Hmm.
solid inorganic compound which consists of at least one non-metal or metalloid. If all the constituent elements are metals, then that material can no longer be termed a ceramic. So first of all, it has to be a solid inorganic compound,
Hmm.
and then at least one of the constituent elements has to be a non-metal or metalloid like silicon or let's say arsenic, things
Hmm.
like that.
Okay.
So, as far as ceramics are concerned, they have, you know, very high melting points,
Hmm.
and we usually, I mean, there are many ceramics for which they have to be annealed at very high temperatures
Hmm.
to form that crystal structure which we are aiming at. People can anneal it at 1400 degrees Celsius or let's say 1600 degrees Celsius, very high temperatures. So, higher the temperature at which you are annealing, higher will be the grain size. Because you see, at higher temperatures, the diffusion coefficients of atoms, they are very high. So atoms can migrate to
Hmm.
new locations very, very easily.
Okay.
And you see, grain boundaries,
Hmm.
the boundaries between grains, they basically have high surface energy.
Hmm.
So the material is always trying to reduce its Gibbs free energy.
Hmm. Hmm. Hmm.
So you see, these high surface energy regions contribute to a higher value of Gibbs free energy, and by eliminating these grain boundaries, you get a lowering of Gibbs free energy, which is thermodynamically favorable.
Hmm.
So
Hmm.
at higher temperatures, the atoms have the freedom to migrate, and smaller grains can consolidate into bigger
Bigger
grains,
grains. Okay.
so that these grain boundaries are eliminated and the Gibbs free energy is reduced. So grain growth always happens at higher temperatures.
Hmm.
And higher the temperature of annealing, higher is the grain size.
Okay.
So yeah, that is the thumb rule with which you can predict what kind of grain size the material will have. So let's say there is a ceramic material which you synthesize by annealing at 800 degrees Celsius, and there is another which you synthesize by annealing at 1500 degrees Celsius. So the one which you are annealing at 1500 degrees Celsius will have a much higher grain size. Yeah.
Okay. And I believe there are also efforts going on towards building single grain materials as well, right? Be it metallic or even non-metallic compounds.
Yeah, there are certain applications where there is no option but to deal with single crystals or monocrystalline materials. So
Okay.
the opposite of polycrystalline materials is monocrystalline materials. So there is only one grain or one crystal in that block.
Hmm.
And yeah, I mean, making that is challenging, but it depends on the application. Like there are some applications where grain boundaries play a very, very detrimental role,
Hmm.
and you simply can't afford to have grain boundaries. So you cannot afford multiple grains. That is
Yeah.
simply not an option. So yeah, it depends on the application whether you deal with monocrystalline or polycrystalline materials.
Hmm. And I think the grain boundaries are the source. I mean, are the regions where you even have your material failures, right? Under tensile loads or even shear loads. I think those are the grain boundaries. Is where the fracture or any tear also happens, right? It doesn't happen through the grain.
Uh, well, I am not that well versed in mechanical properties,
Hmm.
so I am not the best person to answer this. But yeah, I will try to give a reasonable answer. So the thing is, if you are talking about breaking point of a material, which is the maximum strain which the material can take before breaking into pieces.
Hmm.
So the breaking point depends on the like at what strain the first cracks start appearing. So what happens is, as you go on increasing the strain in the material beyond a certain value of strain, very small cracks appearing within the material, and then these cracks grow bigger and propagate through the material. Now, the basic science is that when a crack is being formed, new surfaces are being created. You understand that, right?
Yeah, yeah, yeah.
Previously, that material was continuous, but now a crack has appeared within that material. So there is essentially a region of vacuum within
Hmm.
that material because a crack has appeared. And I mean, with the passage of time, gas molecules from the atmosphere can diffuse into that crack. That's a separate thing.
Hmm. Hmm.
That might take time, but essentially you are introducing a region of vacuum within that material when a crack is being formed. So you are introducing new surfaces.
Hmm.
And higher is the surface energy of that material, more difficult is the formation of cracks. So cracks won't form to begin with if the surface energy is very, very high. and that is good. Means it means that the material won't break that easily, because it is very difficult to form even small cracks at the first place,
Okay.
because the surface energy is high. So yeah, people calculate these kinds of things, and they
Interesting.
can find out. Yeah.
Interesting. This has taken me back to my mechanical engineering days where we had a course on material science with, I think the reference book was McAllister's about material
Yeah.
science. Right? So I think we had some relationship between grain size versus material strength. And there's some proportionality or inverse
Yeah,
proportionality.
the yield
Ah, yield
strength
strength.
definitely depends on grain size. Like as you go on decreasing the grain size, the yield strength goes on increasing. So it becomes very difficult to introduce plastic deformation
Okay.
in the material.
Interesting. So, anyone has other questions? I've been hogging most of the time. Okay. So, and the other thing that I also wanted Smarak to help out with is to also give out a very brief overview on how someone could start with material informatics, right? And why it matters. And
Yeah,
yeah,
yeah. So I would say that materials informatics matters because for a very long time, material science has suffered from a unique problem, a unique problem. So, there are way too many materials engineers who, you know, they operate in a completely hit and trial fashion. Like they go to conferences, talk with fellow researchers, and they will tell, I you mixed material A and elements A and B to synthesize this compound. Let me try A and C. And, just mix different stuff. Just mixing random ingredients like a cook does, to see what changes happen. So this random hit and trial stuff, random mixing of ingredients has gone on for too long, and that needs to change, in my opinion, because if look, let me give you an example. There is a certain class of ceramics represented by AbX3, where A and B are cations and X is an anion. These are called perovskite ceramics, and they are very widely used in many kinds of applications. Now, the point is there are unlimited permutations and combinations. A and B could be any cation, and X could be any anion. So you can have so many combinations, right? And you can just do hit and trial experiments, synthesize new materials just based on whims for throughout your life. But that is not really efficient. What we would like to achieve, like the ultimate achievement for the materials informatics community, will be to get rid of this hit and trial business. Like if we are able to predict that uh, what kind of anion is likely to enhance property X or property Y, then you can work specifically with that anion. AbX3, X is the anion. You can work with a specific anion if you know beforehand that this anion will give good value of property X or property Y. And it is very difficult to achieve this because it requires enormous depth in materials informatics to reach that stage. But that is the ultimate goal which scientists are chasing. And if in the future we are able to achieve such insights, then we can save a lot of time. We need not synthesize random materials just based on whims. We can stop being whimsical and be more targeted in our approach. And for that matter, I should also highlight the kind of skills which are needed to succeed in this field. First of all, statistics. No matter which area of science or engineering you are from, doesn't matter what your bachelor's degree is. You need to have a strong grounding in statistics because data science is all about extracting insights from data sets. And right now, the problem in many engineering departments is that there are many PhD scholars who do not focus on developing these skills in statistics. They don't have a solid grounding in statistics and they are not being pushed in that direction. So ultimately, what ends up happening is a lot of research papers which are, very trivial, which come out. So if you have a strong grounding in statistics, you will go a long way. So I think that that is something which you should start with. You should also try to achieve some basic understanding about ML algorithms, how they work, and in what kind of situations they can be used. I understand that you cannot go too deep into the mathematics of these ML algorithms because that itself is a whole different world. And if you are a material scientist, you basically have to focus on materials. But some understanding of the working of ML algorithms is something you should get, you should spend time on. And then finally, I will return to that slide. Uh, yeah, so the factors affecting the accuracy of property prediction. So the second point is the choice of features. Uh, so using unnecessary features or descriptors is a problem, but even if you are using a lesser number of features, it doesn't mean that you end up getting high accuracy because you might not be choosing the right features. So, you know, what is the thing which enables you to choose the right features? That is the question, right? And the answer is a very strong uh, understanding of the underlying physics of the problem which you are dealing with. For example, uh, magnetic properties of materials are, they are very complicated to study because you need to have a solid understanding of quantum mechanics while dealing with magnetic properties. That is not necessarily true for all kinds of properties. For example, if someone is dealing with thermal properties and let's say they are studying things like thermal conductivity, coefficient of thermal expansion, you know, they can probably get away without understanding too much of quantum mechanics. But for people studying magnetic properties, there is simply no escape. Uh, you need to have a solid understanding of quantum mechanics to understand phenomena like exchange coupling, exchange energy, correlation energy, strongly correlated electron systems. Like these are things you cannot hope to understand by not mastering quantum mechanics. You have to do the hard work. You have to spend the hours and days and months to master those skills. So you have to understand the underlying physics of your problem. And magnetic properties is just an example. If you are dealing with magnetic properties, you have to master quantum mechanics. If you are dealing with mechanical properties, you have to master dislocation theory, which is a nightmare for many researchers because it is exceedingly hard to understand. Dislocation theory is exceedingly hard to understand. It involves a whole lot of complicated stuff, but you have to spend the hours and days and months if you know want to reach that stage, because only when you understand the underlying physics, you can choose the right features required for developing a good ML model. That is not true for experimentalists. For example, there are many engineers who do purely experimental work, and that is true for materials engineers as well. There are many materials engineers who spend their entire PhDs doing only experimental work. So they might get away. They might get away without going very deep into the physics of the problem. They might think that, okay, I'm not a physicist, why should I care? And they might get away with that. But if you are in materials informatics, you cannot get away with that. That is what I'm trying to highlight over here. Because uh, choosing the right descriptors or features is a very challenging problem, and you need to understand the underlying physics. If you before you develop that skill of choosing the right features or descriptors, and you are always welcome to explore certain videos on YouTube on physics informed machine learning. So there are, I think, some YouTube channels which have a lot of videos on this topic, physics informed machine learning. That is something which people are actively exploring right now, because they have discovered that without understanding the underlying physics, you won't get very far. So physics informed machine learning is very important in my opinion. And in a nutshell, if were to summarize what kind of skills you should be acquiring, certain skills in statistics, a good understanding of the underlying physics of your problem, and also some basic understanding of the ML algorithms which you are dealing with. You cannot hope to go very far by randomly playing around with random algorithms. That won't take you very far, and that is easier said than done. It involves a lot of hard work, but yeah, that is what I have realized.
Thank you, Smarak. Yeah, that was very informative, very insightful.
Yeah, I'm very happy to share all this.
I hope like even I think we had a good audience, and I think we're going to have a lot of undergrad students and upcoming researchers really benefit from your talk, because I think these are some insights that we need to keep in mind when we're starting our research in material informatics or even trying to explore this domain, right? I think you have really put them in a very nice nutshell, uh, and I really we all really enjoyed the talk. And
Yeah, very happy to know that.
yeah, so thanks for your time, and yeah, also tell us a bit about uh, where you're heading out for your postdoc.
Yeah, I'm heading out to Germany for my postdoc. This is a university named Brandenburg University of Technology. I have got a position in the research group of a prof who works in the physics department of that institute, and they work primarily on photonics. And photonics is basically the field in which people try to make these photonic integrated circuits. So all of us, I think most of us, are familiar with integrated circuits or semiconductor chips, which is the alternative name, in which all the circuits are based on electrical signals. Basically, they depend on the flow of electrons. Photonic integrated circuits are, they are chips where the same functions are achieved using optical signals. So they use optical fibers and other components which are useful in manipulating optical signals to achieve similar objectives. So photonics is also a very active area of research, and people from multiple engineering and science disciplines can go towards that.
Great, yeah. Thank you. So we'll conclude the session now,
Yeah,
and we hope to see more of you in other sessions as well, where we'll possibly discuss photonics in detail and even possibly just do a deep dive brainstorm, read a paper, a very recent paper in material informatics. I hope we do that sometime soon as well. And
Yeah.
so, yeah, thank you so much. And thanks everyone for attending. And I hope this session was insightful for you and you have something to take away with regard to how you can think of any machine learning problem in a very complicated or complex or very challenging core scientific or engineering domain, right? I think it's important to bridge the gap between the two. And that was really well encapsulated by Smarak in this talk. And I would like to close by saying that we have Dhyuti Labs, which is like a sandbox, GitHub open source community initiative where you could come sandbox some of your ideas and also look out for certain micro challenges we keep putting out there, and also some of these good first issues for first time open source contributors who would like to get their hands dirty and contribute to an open source package or a problem or challenge, right? I think this would be a very good opportunity for those. And also, we have a growing WhatsApp community, and you could join this group and stay on top of scientific machine learning literature, walkthroughs, announcement about activities such as Dhyuti Spotlights, and so on. And stay tuned for more such activities. We're going to have a couple more talks this month, and we're going to soon have Dhyuti walkthrough on operator learning. So last time we had a walkthrough in physics informed neural networks. We're going to have a walkthrough where I'll be taking you through what it looks like to train an operator model for different domains. And the subsequent month in December, we're going to have a couple of series of mini symposium type sessions, which I'm going to be calling them as Dhyuti Sparks. So we're going to end up this year with 4 formats that we would have launched. One is Dhyuti Talks, one is Dhyuti Walkthroughs, and Dhyuti Spotlights, which we are very fortunate to launch it with Smarak. And finally, Dhyuti Sparks, which is going to be on a very interesting topic. Stay tuned. Thank you so much.
Thank you. Thank you for this opportunity. Okay, guys, it was great interacting with you.